Now, I'd like to follow up with other people's comments. My congratulations to Larry. I was trying to think back, and I know it's been at least 25 years, and we could go back 30 years. And I've always had the tremendous amount of respect for Larry and his ability to couple superb instrumentation skills and experiment, but with this solid fundamental understanding of the physics of the phenomenon. And that's been characteristic of all his work over that time. And it's really, really pretty special. And this has been documented, and everybody has seen all the contributions he's made. I'd like to address a couple of other aspects of Larry, which I think are equally important. As a person and a scientist, he has an unbelievable degree of perseverance. And the VCD community, I was never part of it, but the word pariah comes to mind in the first years of this. This was a small group of people who routinely got together at Ohio State. And they were given a room on Thursday afternoon after most people had left. But they kept at it. And a lot of that was due to Larry. And it wouldn't be where it is today if he didn't have that degree of perseverance. So that's one aspect. Another one is he has a very good sense of dedication and responsibility to the community. I know Larry worked on the Cobalt Society, he worked on SAS, he's a wonderful mentor. Anybody who can be department chair for 16 years, has to have a sense of duty or nothing in the cerebellum. I mean, he's got to be brain dead to do it for 16 years. And he did it, and he did it very, very well. So those aspects are really something. I also owe Larry a debt of gratitude because he helped Bill Harris and I get payback on somebody. There's a young lady named Jerry Richmond. Many of you know Jerry. And one time, and this has to be 22 years ago, Bill Harris and I were at the Asilomar conference, and we decided to go out running with Jerry. This was a big mistake. Jerry humiliated us, left us in the dust on this beach, laughing at us all the time. Okay, so we had to get back at her. You hadn't met Jerry at that point, and we said, hey, there's somebody else who'd like to go running with you. We didn't mention that Larry was a marathoner. And Larry went out and ran her butt into the beach. And he totally humiliated her. And I really still appreciate you doing that. So again, congratulations, Larry. What I'd like to talk about today, again, there's actually going to be a minimal amount of vibrational spectroscopy, a little bit in here. But it's work that we've been doing in John's research group, which I helped direct the students, on a concept known as electrospinning. A lot of acknowledgments here. You're going to be seeing results from the people at ANSYS, Dave Martin on some electron diffraction, a lot of people. And again, many of the slides, the great thing about working with John is we prepare talks and then routinely exchange slides. So it doubles the number of slides that you can pick for a given talk. Many of these slides originated with John's work, so thank you. So quickly, what is electrospinning? It's a fiber forming process that actually was discovered, I think, in the mid-40s. Died for a long time and has experienced a real renaissance in the last 10 years, maybe 15 now. It is now marginally commercially viable, but it's been extremely interesting because it's a route to produce fibers that you can put the word nano in front of. And basically, it's either a solution or a melt spinning process. But what it consists of is a reservoir, say, of solution that passes down through a needle, and there's a sufficient essentially pressure on that syringe, not to force it through the needle, but just to produce a continuous supply of liquid that forms a hemispherical drop, basically at the end of that liquid. If you now start to charge that, multiple 20 kV above ground, at some point, automatically by itself, you'll start to get a filament that forms and then transits to the ground plane. And that filament forms because you get a buildup of electrostatic charge on that droplet. The droplet deforms, and as it goes to a point, eventually electrostatic propulsion is going to eject a filament away from that residual drop, and that filament essentially can be very, very small. So that's the basic concept. The parameters are, many. Obviously, solution viscosity, molecular weight is going to play a role. The conductivity of that solution is going to play a role because you've got this essentially voltage potential across here. You've got to be able to essentially have that solvent flash off to go from a solution up here that's coming down off of that to dry fiber down here. So there are things that we can control to change things like the fiber diameter, the density of fibers that spin down in this non-woven web, and all sorts of parameters. So basically, what this thing looks like, and this is courtesy of Darryl Renneker, and I hope the movie runs. That's what an electrospinning in rapid time looks like. It looks like you've got a whole bunch of different filaments. That's actually a single filament that's just whipping back and forth. And it plates down, so if you think about it, that particular non-woven mat, in the best of cases theoretically, is one filament that's winding around. But that whipping action that occurs after the straight region provides both shear and elongational forces, so the fiber diameter really starts to neck down at that point. And as the fiber diameter gets smaller, it becomes easier to lose that solvent, and that's the transition where it dries out. The bottom line is you can produce fibers that are literally as small. I think the best we've ever done is about 50 to 70 nanometers, and you can routinely produce fibers that are just hundreds of nanometers in diameter. This is in contrast to commercial melt spinning or solution spinning where the fibers are tens of microns in diameter. So you're down to this small scale, which has a lot of potential application. That just gives you the scale of a human hair versus electrospun fibers. This process generated a lot of interest, and everybody, started going through their shelves and electrospinning whatever polymer they had and writing a paper that we can electrospin 2,4-dimethyl chicken wire. Our approach has been a little bit different. We're trying to understand the structural concepts that occur when you spin these fibers. Do you produce something that is fundamentally different than you get when you solution spin or cast a film? And can we use the different operating parameters in electrospinning to change both the structure and morphology in the filament itself to change the properties? It's a fundamental tenet of polymer physics, in this case, that the macroscopic properties, which may be important in the use of this material, whether it's the tenacity, the modulus, the stiffness, the elasticity, all these things must have at their very base concept things that are happening at the molecular level. So a couple of questions that I'm going to try to go through today. Hopefully I'll get through them all, but when Singh starts unplugging the computer, I'll stop at this. Are these sorts of questions? So the first one is, orientation is critically important in polymeric fibers. If you want to get high tenacity or high modulus, you've got to have chain orientation. It's just about impossible to get that without it. So orientation is important. Crystal form is important. So can molecular orientation be induced during this electrospinning, and can it be retained? Do those non-woven filaments actually contain chains that are oriented in that fiber after electrospinning? Well, it turns out there's a way to electrospin not onto a full ground plane, but onto a gapped ground plane. So if the ground plane here is aluminum foil, and this is the thing that's sitting back here, if we spin onto that ground plane, you find something very interesting. You find that in the gap, the fibers are macroscopically oriented across the gap. If you look away from the gap on just the aluminum foil, they're randomly oriented. Well, that's critically important if we're going to use a probe that's not capable of looking at individual filaments. I'll get to that in a minute, Christian, that there is a probe capable of looking at it. But if we're looking at sort of a bulk measurement to try to tell whether there's orientation in an individual filament, you have to have a macroscopic collection of the filaments that are oriented. Even if these chains were perfectly oriented in filaments, if multiple filaments are oriented randomly, any probe, whether it's X-ray or Raman or infrared, is going to see that macroscopic averaging and tell you there's no orientation. So by doing this, we're able to look in that region, and you can do simple things like polarized Raman, very simple. We, as a qualitative measurement of orientation, we simply look at the ZZ. So incident polarization is Z, scattered is Z, and YY. If there's no orientation, those two measurements have to be identically the same. If there's orientation, they'll be different. And sure enough, for polyethylene oxide electrospun fibers, there's clear orientation within the individual filaments of the chains if you look across that gap. The same thing for PVDF. If you look off the gap, this is now doing polarized infrared. A neat thing about these non-woven mats is even though you think they're comprised of filaments with pinholes, the pinholes, because the fiber diameters are small enough, the pinholes are way below the wavelength of light you're looking at, so it appears as a film. We don't have a stray light problem. But if you look at the filaments off the gap, lift them off, and do polarized infrared. There's no difference. In the gap, you see a difference. So first question is answered. There's no question but that we can produce orientation in these filaments where the chains are oriented preferentially along the fiber axis if you spin onto a gap. But that raises another question. Is it the act of spinning onto the gap that causes the orientation? For example, does the filament come down and tack to one side of the gap and then from electrostatic forces sort of get drawn across the gap? And is it this drawing process which is producing the chain orientation versus the electrospinning? So we'd really like to be able to look at individual filaments. So how do you do that when it's only 100 nanometers in diameter? We're not going to do polarized infrared. Diffraction limit's going to kill us there, though there is a way to get at it, which I'll talk to about in a minute. Ordinarily, we're not going to do Raman. I will point out that Christian Pellerin has done some very nice confocal Raman within the last year and a half, and he has been able to look at individual filaments if he cheats and uses things with real strong Raman cross-sections. Neither of these two things are strong, the PEO and the PVDF. We've actually made a little bit of an effort, and we can't get enough. So how do we look at individual filaments? One of the first techniques we used, and this was in collaboration with Dave Martin in our department, was selected area electron diffraction. So in the electron microscope, we're going to look at electron diffraction. We can use the electron spot on an individual filament. That's the good news. And if it's oriented, you'll be able to see the diffraction pattern showing orientation. The bad news is that polymeric filaments of a couple hundred nanometers in an electron beam don't last a long time. So you've got to get the data quickly. But we were able, the student who got this was actually able to start to see, there's the diffraction pattern, that's the bright field image. And you can see when she looked at individual filaments, or a group of about 3 filaments, in the gap, where we know from the infrared and Raman there's orientation, sure enough, the electron diffraction starts to show a pattern. Off the gap, you actually start to begin to see, there's nowhere near the orientation, that differential in the intensity, but there is some indication that even off the gap, there's some chain orientation. And she can actually get the spacings from the electron diffraction, and matches with the experimental despacing, the calculated despacing for these crystal structures of PVDF. So again, if you look very nicely off the gap and on aluminum foil, so these are both off the gap and very far off the gap, with 2 different diameter fibers, and the diameter is affected by the voltage that we're spinning on, the viscosity and concentration of the solution, but even that diffraction pattern changes as a function of the size of the diameter. So our ability to orient chains within a filament is a function of the size of the filament that we spin. So it could be a containment effect. It could be the amount of mass of material that's trying to reorient. Smaller fibers, if eventually you get down to single chains, it's going to be easier to orient a single chain than multiple chains next to each other because of chain-chain interaction. And you can also see this again. This is in the gap, where now you see very strong orientation. So there are sort of 2 effects going on. Clearly the gap enhances orientation, but there's some chain orientation even when you're not on a gap. If the gap width changes, it changes it. And this is sort of supportive of this concept of the gap causing a drawing of the fiber as it goes down across that gap. So again, different degrees of orientation. No gap, that's basically the planar aluminum itself. Small gap, bigger gap, the orientation gets bigger as the gap gets bigger. That doesn't happen infinitely. You make that gap too big and they won't span the gap. Okay, that's one way to do it. Another way to do it was done in collaboration with the people at Anisys, who have got this Nano Ir instrument, which is fundamentally, if you haven't seen it before, they utilize an AFM cantilever that's tapping on this particular system. The fibers are supported across the face of a prism, which is undergoing total eternal reflection. They bring in a pulse tunable infrared source. So this comes in, excites an evanescent wave up to where the fiber is, and the AFM tip is sitting on it. Think about what happens when you come in with a pulse of infrared light that's not in an absorption region. Nothing. If it's in a region where it's absorbed, that light gets absorbed into the fiber. There's a heating which kicks that cantilever basically from a thermal expansion and then damps down. So you see ringing of the cantilever when the laser is tuned to an absorption band. no ringing when it's not. You can do an FFT on it, and then you can plot that intensity of the oscillation as you sweep the infrared laser and track out an infrared spectrum. And that's exactly what they do. These are 2 PVDF fibers that were basically electrospun onto that crystal, sent out to them, and you can get essentially a swept infrared spectrum of PVDF in this region. So that was good. The next step, and we talked with them about this, as we said, would really like you to be able to do this with controlled polarization of the light coming into the crystal to look for orientation. You know, again, this is sort of a straight infrared dichroism experiment, if you will. They were able to do that and actually show, first of all, that for an oriented fiber in FTIR, for a bunch of them on the gap, the form of the spectrum in parallel and perpendicular polarization is the same as we get with a swept AFM infrared spectrum, and we can see different intensities for parallel and perpendicular when the fiber direction changes. So this was the ability, gave us the ability to work now with individual filaments in the infrared to, again, show that there is orientation. Okay, I'd like to move on from that now that we've shown orientation. We want to talk about actually using these non-woven mats to do something other than just make measurements on. And one of the programs that we have is trying to basically build bioscaffolds for cell growth. And the reason the nanofibers are great is because by controlling these small diameters, you can produce pores that are the appropriate size for cells to grow and move in and out of our basically three-dimensional scaffold. The problem comes when you think about trying to do that is you've got a couple of different properties that you'd like to tune. You'd like to tune the biocompatibility of the surface of the fiber. You don't want to put in fibers that will kill cells as they grow. That's sort of counterproductive. But you also have to tune the mechanical properties of the fiber to produce a bioscaffold that has enough flexibility that it looks like extracellular matrix. So how do you tune mechanical properties and biological properties in the same chemical fiber, if you will? You don't have the ability to independently adjust them. And this led us to the concept both of coaxial electrospinning, which other people have done. In coaxial electrospinning, instead of one needle, you've got 2 needles. A needle inside of a needle, 2 different feeds, 2 different polymer solutions, 2 different polymers. You feed them down, and if you do it right, you can actually get fibers to spin off that. That individual piece comes down, but it's actually got component A inside of component B, and you get a coaxial structure. And people have used this with the internal feed actually as being something like silicone oil or water. You can wash that out and produce hollow fibers with a coaxial stripe. You can put individual fibers down in there. We wanted to take it a step further, so we asked a student, you know, if you can do it with 2 needles, can you do it with 3? So the student, and this is Wenwen Liu, has actually been working on triaxial spinning, where we literally have a needle inside of a needle inside of a needle, all coming out at the same point. You have to fine-tune things like the viscosities, the solvents. You know, the solvents should be relatively immiscible because you don't want them to mix at that point. You want to maintain that structure, but the solvents also have to be able to get out. So it's a non-trivial process, but Wenwen has actually been able to make this to work. And the reason we want to do that is now we have 3 different, or in our case actually 2 different polymers in 3 different regions, where we can tune one property in one of the polymers, the second property in another. So for example, if we spin something that the outer region can be biocompatible, so that's going to govern the cell growth. The next one down, which the cells won't see because they're covered, could give us our strength. The third component could be something which contains additional agents like growth factors, which when you make this will slowly diffuse out through the tube and enable cell growth. So triaxial spinning, the big plus we think we're going to find in it is the ability to independently tune multiple properties that are needed for the cell growth. So again, a lot of different parameters in here that she's trying to mix. There are relatively unique rules. I guess relatively unique, it's not. Unique rules for triaxial and coaxial spinning to get it to work. You have to be concerned about flow rates being so big that the droplet starts to deform. Or flow rates that are not good enough that the outer ones start to form and the inner one never gets into that stream that's starting to come off. That's perfect. If you have too high voltage drop, you can actually split off and get 2 filaments coming off of this, because the Taylor cone, that bubble can essentially have breakthrough of one of the feeds. But when you get everything right, and that's everything right, she was actually able, we think, to be able to spin gelatin on the outside, polycaprolactone on the middle, and gelatin on the inside. The gelatin on the inside will eventually have growth factors in it. The gelatin on the outside provides the biocompatibility, and the PCL provides the strength and the elasticity. So the first step was to activate just 2 of the 3 needles. So this is the shell was the PCL, and the core was gelatin. These are just SEMs, and those don't prove anything, because when you get into this coaxial and triaxial spinning, the first question is, how can I prove to you that we actually got these structures, as opposed to simply a physical mix of them, or just one coming off of the other one? So this is TEM images, and if you have an imagination, you can actually see a core that appears to be there is slightly lighter, that the electron density provided some contrast there. So is that for real? Maybe. We then tried putting essentially rhodamine B inside the inner one and tried to do confocal microscopy on it, where these are false color images because the fibers themselves are autofluoresce, but the rhodamine fluoresces at a different wavelength. And is there something going on there? Sort of looks like there's a core inside a shell. So this was promising enough that she went right ahead with the triaxial. These are now gelatin outside of PCL with gelatin. Fiber diameters here, there's the micron bar, so these are 700, 800 nanometers in overall diameter. But proving that there's actually 3 layers is challenging. The first thing she did was drop back and say, we've got 2 components in there, gelatin and PCL. The infrared spectra are quite different, not a problem. When she looked at the 2 needles activated, so it's the coaxial and not that, with the PCL on the outside, sure enough, the ATR spectrum of those fibers just smashed down onto the crystal. Not smashed, gently laid down onto the crystal, so you didn't destroy the structure. Looks like PCL. And you'd expect with the evanescent wave probing that the spectrum should be dominated by whatever's on the surface of the fiber, which in this case should have been PCL. When she went to the triaxial and had gelatin on the outside, the spectrum changed to look more like gelatin. So it looks like there's gelatin on the outside. It looks like with the 2-needle system, there's PCL on the outside. So again, we're starting to build the data, but nothing positive proof yet. She tried to do cross-section TEM, and unfortunately did not try to do cryo cross-section TEM. And when you try to cross-section these things, they're soft enough that what you see is tremendous distortion of the circular cross-section of the fiber into these ugly things. Now, does that show triaxial? Who knows? I mean, certainly it looks like you could say it's coaxial, but is there dark, light, dark on the outside? Maybe. I don't know. How many? Are you convinced, Sandy, that that's triaxial? No. But the saving grace was a new instrument which we got in, which was a focused ion beam SEM. And she was able to take these then and put them into the fib SEM. They used the focused ion beam. You can mill that thing right off. Now there's no curving, no slopping over. And again, we might have to put the lights out if you don't believe me, come up close. This now you can see a central core that's lighter, middle, and outer that's lighter. This we thought was now starting to be pretty convincing proof that she's actually been able to do this triaxial spinning. And we're at the stage now we're going to be starting to look at bioscaffolds where we've got this and see if we can do cell growth on it. How am I doing staying on time? Oh, we're fine then. Just making a little switch. The last thing that we've been trying in the group was how do you get around the fact that you'd like to make these fiber diameters even smaller. You'd like to get them down into more controlled areas or maybe even draw patterns of these non-woven mats. If you start to simply make the needle that you supplied the drop from smaller and smaller, which might give you a smaller diameter, the needles plug. You know, you can only go so far with a viscous solution through a syringe. So could we do it without a nozzle, a needle, to try to get increased throughput or possibly even control parameters? And the idea was developed, and I think John came up with that, and I forget who else was the original idea on that. Tom Beebe. Okay, an AFM tip is a needle. We can't supply it on the inside, but what would happen if we literally dribbled the polymer solution down around the outside of the AFM needle? As it runs down, it becomes a smaller and smaller point. Obviously, the electric fields are much bigger because the point's much sharper. What will we get? Can we electrospin by simply feeding it down across the needle and then putting the potential between here and the ground plane? What do we get? Put this whole thing together with a cantilever and the drop going onto that. And what we actually get is electrospinning. This is what he got basically when you did the AFM electrospinning. And that's the size spot with the exact same composition when he ran it with a full needle, way, way bigger. So we've got it concentrated down more. And now you could easily conceive of taking that AFM tip and scanning it to produce a pattern of nonwoven fibers to do as yet undefined other really neat things. We also found a difference in the uniformity. This is the needle electrospinning of a nylon 6 and HFIP. That produces this pattern of fibers that have quite a big diversity or variation in fiber diameter and also have what we call beads, which basically represent electrospinning, which is sort of stopped and turned into electrospray and back to electrospinning. It shoots out a blob the way you would in electrospray. We don't see any of the beads over here in this exact same spinning solution done on the AFM tip. And the fiber diameters are more uniform. The other thing you see, and we had a whole different study that I'm not going into here, on the crystal forms that are created. This again was nylon 6. When you simply solvent cast nylon 6 from that same spinning solution, you get basically the alpha crystalline form, which is the thermodynamically stable crystalline form for nylon 6 as it crystallizes. It's a semicrystalline polymer. If you do conventional electrospinning or AFM electrospinning, you get a metastable crystalline form. The gamma form shows up. And it turns out the reason for this is when you're doing electrospinning for a semicrystalline polymer, you've got two competing processes. The solvent's flashing off. Okay? If you have tremendously fast solvent flashing off, faster than the rate that the chains can essentially reorder to grow crystals, you'll trap a metastable state. So the development of crystallinity is competing with the rate of solvent loss. Once the solvent's off, the chains aren't mobile anymore, and you can't produce crystals, or you can't move from the metastable one to the thermodynamically stable one. So electrospinning produces a metastable crystalline form, but even within that, there's a difference between the AFM electrospinning and the conventional electrospinning. The AFM produces basically smaller crystallites. You get more points of essentially seed crystallization occurring, so you get a whole lot of little crystals rather than more big crystals. And little crystals are nowhere near as perfect because they've got more surface. There's also a difference in the DSC showing that there's a suppression of the enthalpy. There's a shift in the temperature. We haven't answered this question yet. Is it simply poor crystal development, or is it actually a confinement effect in these smaller fibers that changes the way the crystal melts when you do the DSC? So this is offering a fair amount of promise in terms of creating, again, through processing, different properties for the fibers, different properties for the mats, potentially different applications. So basically we've gotten to the point now where we're starting to get a handle on the ability to control the molecular level properties and the macroscopic properties of the individual filaments in the mat. This is going to play a role in how effectively they form bioscaffolds. It's going to play a role in how effectively you can create nanofiber mats for filtration. One of the reasons we're interested in PVDF is PVDF, if you get the right crystalline form, is piezoelectric. You could think even of having a filtration mat that under the effect of an electric field changes pore size and cleans out and then comes back down. Because you drive the fibers that are piezoelectric, you change their dimension. We've done some single nanofiber characterization with both selected area electron diffraction, the ANSYS polarized Nano IR. We're following up Christian's work on trying to do confocal work right, and as he has done, and you can get decent, very decent orientation information on single filaments there, and we've demonstrated the triaxial electrospin. So it's been a fun area to work in. We like to think that we've gone beyond simply just spinning fibers for spinning's sake, trying to really control the properties of what we're producing to essentially facilitate end use of these. At this point, I'd just like to again congratulate Larry. It's really great to see him be recognized like this. I appreciate all that you've done. I should have said one other thing about Larry's personality, which is also very good. This is one very level guy. Okay, I've never seen him get super excited about anything, and I can't ever imagine him kicking the hell out of the file cabinet in the office when something goes bad. And this has stood him in very good stead, because one common area Larry and I have is the enjoyment of collegiate basketball. And if you're unfortunate enough to be a Syracuse fan, you better not react to the highs and the lows, because this is a team that's all over the place, and he's been very good about that over the years. Larry, congratulations. Thank you very much for your attention.
Thank you very much. We do have time for quick questions or comments.
Yes.
Is there any way to introduce chirality?
Why would anybody want to work with chiral materials, Larry? I don't understand this.
You're spinning. What spins? Does it spin one way?
This is the problem with an engineer's definition of spinning and your definition. Spinning, you actually think it has rotational motion. Fiber spinning is like a spider spinning. There's no rotation. Spinning is the term applied to essentially taking a solution or a melt and producing a fiber. So all of the motion basically is axial. And the forces that are involved are primarily elongation for the whipping. There's some shear involved, but there's no rotational spinning in that sense. No, the movie, it didn't have a turn. That was actually the fiber whipping this way, whipping that way, whipping that way. It's whipping so fast, the camera said, hey, this is all a mess.
But what about actually starting with a chiral polymer? And it might be interesting for biocompatibility.
Well, this is an interesting question. What you're raising is, does the chirality of the scaffold affect cell growth? And I don't know that anybody's ever looked at that.
You have to make an isotactic regular chiral polymer, like every monomer unit,
and
making up has a chiral element.
Yeah. To be honest, I don't know, and John or anybody else jumping in here, I don't know that anybody besides Mother Nature can make a chiral polymer.
Well, you can make chiral polymers.
Well, one of the problems is, the polymerization process in these sorts of polymerizations is not well controlled. You can get head-to-head. If it's a vinyl polymerization, you can get head-to-head, head-to-tail.
If the side chain is chiral, for example.
If the side chain starts out as chiral, and I think you're still going to be concerned about the tacticity of the side chain off of the backbone. It would be interesting to try, but the answer is no. We've not even thought about it, and I don't know of anybody who's done it. Howard?
I was wondering, can you actually go on the next step and try putting some cells on one of these Macs and see what happens?
Oh, yeah. Tomorrow morning. in Ira's session on vibrational spectroscopy biology, we and several other groups have already tried to do that. What are you saying, Christian? But we have grown bone osteoblasts. There's been some growth of cardiomyocytes, cancer. One of the issues about that is that to test cancer drugs, you start off with tumor cells, right? But the historical way to do it is on flat plate polystyrene, growth gels. And that produces the pseudo-tumor that's two-dimensional in nature, which isn't what goes on in your body. So that's one of the things about these cell scaffolds that we have are three-dimensional in nature, so it produces something more realistic. And we have one student who actually showed the efficacy of an anti-cancer drug on some cancer tumors varied depending on whether you grew those tumor cells on a flat plate or on a cell. So yeah, we have done. The cardiomyocytes are sort of cool because when we've grown that, cardiomyocytes are the cells which develop into the heart muscle and deep. And cardiomyocytes, when you put them down on this and they start to grow in selected regions, they will start to beat. You'll actually see the cells move, but they're uncoordinated. As the cells' growths get closer together, they interact and all of a sudden produce a coordinated. It's really cool to watch in the microscope.
Okay. Well, thank you very much, Bruce.